special homework 3.
You want to, I'm so sorry. It was talking when you said that. What's your
Um,
question?
the special homework 3, or like I had.
Sure. Yeah, let's look at special homework number 3. That's a great idea. So shall we look at those? Is there a particular problem or um, do we just want to go through, several of them or let's bring it up.
Mm,
Let's take a look at it. Let's look at the
The
parameter.
first one, okay.
Which one are you looking at?
The part 4, like I didn't get it right. How to like had added there other things. So number 4, that's the one like I want to work on it, and number 3 too.
So is that okay, so number 3 and number 4?
Yeah, the other one is like it's fine, but
So on
we
number
can work.
3, we're going to draw a circuit, right?
Yeah.
I'm going to pin this. So we're going to draw a circuit. And what does it do? It outputs a 1 if and only if P and Q have the same truth value. Is that what it is?
Yeah, let me see it.
I'm bringing it up too. I just want to read it exactly the way it says. Draw the circuit having two inputs, P and Q.
And if and only if P and the Q have the same value.
That outputs a 1 if and only if they have the same truth value. The easiest way to do this might be to make the IO table first.
Mm.
So, it's just a suggestion is to make the IO table first. All right, so let's do that.
Mhm.
Make sure this isn't focused. There, that's better. Okay, so we've got P, we've got Q, and then we've got output S. You agree?
Yeah.
All right, so let's set up the truth table in canonical form. It's 4 rows because we have 2 inputs, P and Q. So under P, we put 1, 1, 0, 0, like true, true, false, false.
Mm.
And under Q, right, we put 1, 0, 1, 0. So we have these 4 rows. Which rows should the output S equal 1?
The first one,
Yep. But also
and there is gonna be two. The one.
the 4th one, right? Because either P and Q can both be 1,
Mm.
or P and Q could both be O. So remember, these rows are input states. What do I mean? When we look at the inputs, P and Q, together, they constitute what is called an input state. In the first row, P is true and Q is true. They're both hot. So this first row is represented by P and Q. The second row, P is true and Q is false or cold. So P and not Q. See where I'm going with this?
Yeah.
What about the third row? How should we label it?
Not P and Q.
Yep. And what about the fourth row?
So it's not P, not Q. Yeah.
And
And
not
yeah,
Q. Yeah, because they're happening at the same time.
yeah,
It's ands
yeah.
across the row. So the Boolean expression is supposed to tell us exactly when we're going to get an output of 1. Well, we get it when P and Q are both true, or there's an or between that and the other situation when we want to get a hot output.
Okay.
Does that make sense?
Yeah.
See, once we see the Boolean expression, it can be a little easier sometimes than to say, oh yeah, okay, I know how to draw circuit for a Boolean expression. We're going to have P and Q. So one of the times we want to get a 1 is if they're both 1. Well, the AND gate tests for that. Do you see how this is going to output a 1 only when P and Q are both 1?
Yeah.
So that's going to get us a 1. But the other thing that's good we want to get us a 1 would be if P and Q are both O. Well, O doesn't help us get a 1, but if we change the O's to 1s with NOT gates, because the NOT gate will flip an O to a 1, right? So P is O and Q is O,
Okay.
right? Then when we put the O's through these NOT gates, they flip to 1s, and then the AND gate will test for that. And it'll output a 1 exactly when both of these are 1. And that happens if they went in the NOT gates as O's. Does that make sense?
Yeah.
And then the last thing we do is we OR those together, because we want a 1 to come out if either this was a 1 or this was a 1. Like you can test for the other two and make sure that they don't output a 1. Like when if P was 1 and Q is O, you get an O out of here, right? If this is a
Yeah.
1 and O, you're right, you get an O out of here. So the output would be O. Same way if P is O and Q is 1. We get an O here, but we also get an O here. Maybe I should put all 4 here. 1, 1, 1, 1, and then so it gives us exactly what we want. It gives us a 1 if they were both 1. It gives us a 1 if they were both O, but it gives us an O if they had opposite truth values. Does that make sense? So this is row 1 is in red. Row 4 is in blue when they were both O's originally. And rows 2 and 3 output an O. Did I show enough work in here?
Yeah. So yeah, it is.
Does that make sense?
Mhm.
So if the 1 comes through here, it comes out as an O. If the O comes through here, it comes out as a 1, but that's still not enough to get a 1. It makes it an O. If the O comes in here, it comes out as a 1. If the 1 comes in here, it comes out as an O, but O ended with O is still an O. So I didn't do them in the same order as here, but you know, it is all 4.
Yeah. Makes sense.
Good. So this is also the same as P if and only if Q. This is what P if and only if Q looks like. So you could have written this or this. It's the biconditional. The biconditional is true when P and Q have the same truth value, whether they're both ones or both O's. P if and only if Q outputs a 1. All right, so now 4 is one of these full adder, half adder problems. Are we ready to look at 4?
Yeah.
Great. So 4, we're going to construct a circuit to perform the binary addition, and we're going to show the work the way that we did in class. Use adders, okay? We're going to use full adders and half adders only. We're not going to use AND gates or gates. We're just going to use full adders and half adders, okay? All right, so I'm going to space this out. I'll do it over here. It's P, Q, R plus S, T plus U plus V. I'm putting some space in between these rows so that we have room. So we always start adding in the rightmost column. The first thing that we can do is we can add these 3 together. Because they're in the same column, we can add them together. So the first thing, right? You see that?
Yeah.
So R.
So we start from R.
Yeah.
Okay.
Yeah. We can add 3 digits together. That's the most we can add together at one time. It's 3 digits. Do you remember which adder adds 3 digits together?
4.
Yep. So we run them through a full adder, okay? Now we're going to get a sum digit out. We'll call it sum 1. And we're going to get a carry digit out. We'll deal with that in a minute. Where is the sum digit? Well, sum 1 stays, the sum digit stays in the column where it was generated. Because the carry digit goes 1 column to the left.
Let's see what.
See, the sum and the carry are always in different columns if they're output from the same adder. That's why it's called a carry. It's going over 1 to the left.
Okay.
All right, now this sum digit, sum 1, is in the same column with the V. So we're going to take these 2 and add them together. So we're going to put V in here now, and we're going to add it with sum 1. It's only 2 digits, though, so we don't need a full adder. We could use what's called a half adder, because that's what a half adder does. It adds 2 binary digits. We'll deal with carry 1 in a minute. Whiteout helps. All right, so when we add these 2 together, we're going to get a sum digit, and that's it. That's called sum 2, and it is a final output because you see there's nothing else left to add to it. So sum 2 goes right here. That's why I'm putting a circle around it. Okay. The carry digit, I'm going to stick it in here. It's just, you can put it anywhere. I'm just putting it in the first place I've got room. Carry digit is over in one column to the left. That's what happens to carry digits. They're always 1 column to the left.
So it's under Q or is?
I'm putting it between the Q and the S, but you could put it under the S. It doesn't matter. The point is it's in the same column with carry 1, Q, and S. They're all in the same column together. Does that make sense?
Yeah.
So here's carry 1, and here's carry 2 coming out of that half adder. And we're going to add carry 1 and carry 2 to the Q, okay? Because they're kind of grouped together. Let's add them together. Doesn't matter what order we add these digits in this 2's column together. We just, eventually, they all have to get added up. So I'm just going to go ahead and just do them C1 plus Q plus C2. But you could add C1 plus C2 plus S, or you could add C1 plus Q plus S, and the C2 could be down here. It doesn't matter. The point is we're going to have to add all of them up eventually. So we've got the C1 wire coming out of the first adder. We've got the carry 2 wire coming out of the second adder. And now I'm going to add them to Q. So here comes the Q wire coming in here. See what I mean?
Yeah.
And these are going to all get added with a full adder because it's 3 digits being added. Now, a sum digit is going to come out of here. It's going to be sum, which one? Sum what? What's the index? Sum 3. And it goes here. It stays in the column where it was generated. Carry 3 is one column, to the left. So here's the carry digit. We'll deal with that in a minute. In a minute, we'll have to add it to P, okay?
Okay.
But this sum digit is in the same column where it was generated. It was generated by adding C1, Q, and C2. See what I mean? So it stays in that column. Now, if there wasn't anything else in this column, we'd be done. It would be a final output, but there's still another digit in this 2's column, namely digit S. I probably should have used the letter S, but oh well. Here's S. It has to get added to the sum 3. And it's only the 2 digits left in this column, so they can get added with a half adder. Does that make sense?
Yeah.
And they're going to have a sum digit, S4, that stays in that column, but it's the last digit in the column, so it is a final output digit. Whereas carry 4 has to come over 1 column to the left, just like carry 3 had to.
Okay.
Right, so here's carry 4. And now here's carry 3. And what else is in that column that has to get added with carry 3 and carry 4?
C3?
Yeah, now see, because so we work right to left instead of working across. We work first column to the right column, then the next column to the left of that, then the next column. So P is the last input, and it's going to get input with carry 3 and carry 4 because they're all in the same column together through a full adder because it's 3 digits.
Okay.
Right? Does that make sense?
Yeah.
And we have sum what and carry what?
Sum 5.
Yep.
And carry 5, right?
Yep. And they should always, these indexing numbers, like coming out of a single adder, the indexing numbers always match. Like out of the first one, it was carry 1 and sum 1. Out of the second one, it was carry 2 and sum 2. Right? It doesn't matter which one goes on top. The point is you got to have 2 outputs. But the sum digit, we know, stays in the column where it was generated. So there goes sum 5. And the carry 5 is over 1 digit to the left. 1 column to the left, sorry, column. But there's nothing to add it to, right? So we're really just adding it to 0. So we just bring it down. And there we have it. So would you like me to give you a practice problem to work on that, you could bring to the Sunday office hour, or, you could email me about?
Okay.
I'll give you a practice problem.
Okay.
So I'll give you a couple of problems and the same instructions as problem 4, special homework 3.
Yeah.
So I don't have to write them all those instructions down. I'll just give you 2. A, P, Q, R plus S, T. Actually, I don't want to use S. I'm not going to use S. P, Q, R plus T, V plus W, X. And then we could just do P, Q, R plus W plus T plus V. So that's 2 more problems you can work on. And if you want to send me the solutions that you come up with, I can check them and see if they're right.
I can email you and we come to the office hours on Sunday night.
or you can bring them into, yeah, just eat. Yep.
Yeah, thank you.
You're so welcome. I'm so glad you asked. Any
Mm.
other questions from homework 3 before I ask Sophie if she has questions?
Mm, So for the number number one, like
Uh-huh.
I get the some part of the drawing, but like I didn't get how to do the table for it, the part B.
Okay, making the IO table for that Boolean
Yeah.
expression.
Mm,
So
yeah.
again, we're working on special homework number 3 right now, Sophie, and now we're going to look at problem number 1.
Okay, that sounds good. Because I had almost the same question.
So the Boolean expression is this. It's P and Q and R, or P and not Q and R, or not P and Q and R. Not R, excuse me. The beauty of this particular expression, Boolean expression, is it is in what we call disjunctive normal form. Let's just review that. It's a really useful form. Anything that's in what we call normal form, whether it's a Boolean expression or a push-down automata, or there are lots of normal forms in computer science. But the reason it's called normal is any Boolean expression could be rewritten in a logical way in disjunctive normal form. And it's called disjunctive because the last operators that operate are these OR operators. Inside the parentheses is a full description of the input. This says P and Q and R are all hot. This parentheses says P is hot and Q is cold and R is hot. See what I mean? And inside this parentheses in this input state is that P is cold and Q is hot and R is cold. So it's normal form because you can always get into this kind of form where you have a full description of the inputs that are getting ORed together. And it's also extremely useful. And one of the reasons why it's useful is we can go directly from disjunctive normal form to the IO table without thinking too hard. So we know we have inputs P, Q, and R because those are the only letters we see. So we know we're going to have 3 inputs, P, Q, and R. So we know right off the bat that our IO table is going to have 8 rows. We have to make the rows even for the instances or the input states when the output is cold. But remember, when we set up our IO table in canonical form, we always start with 1s at the top of our inputs. So under P, it's like true, 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 false, 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 false. Well, true is 1. So it's 1, 1, 1, 1, 0, 0, 0, 0 under P. What would go under Q?
Yeah. And 1, 1, 0, 0, 0, 8,
Good.
and 1, 1, 0, 0.
Perfect. And then under R?
1, 0, 1, 0, 1, 0, 1, 0.
And this way we don't miss anything and it always makes sense. And see, we know we can describe each of these rows is an input state. Row 1 says, hey, we're inputting a hot wire for P and a hot wire for Q and a hot wire for R. In other words, it's P and Q and R. That's what row 1 means. And that's one of the expressions here. This says we want to get an output of 1 if P and Q and R are all hot, or if P is hot and Q is cold and R is hot, or if P and Q are P and R are both cold and Q is hot. See? So it tells us exactly the rows in the IO table where we want to have a hot output of 1. Which row is the row where it's P and not Q and R?
Rotate.
That's exactly right. P is hot and Q is not hot. It's cold and R is hot. So we want a 1 in the row 1 and we want a 1 in row 3. There's one other row where we want a 1. It's if P is cold and Q is hot and R is cold. What row is that?
4, 6.
That's exactly right. And that's the beauty of disjunctive normal form, is because it's really easy to go directly from the Boolean expression to the IO table. And now we know that there are O's everywhere else. See, this Boolean expression tells us exactly when we want hot output.
No, so whenever we have to put 1 on it.
That's correct.
Okay.
If you see this expression, it's one of the times when the circuit should output 1. And that expression is this row. This describes that input state. P is hot and not Q is hot, but that makes Q cold. See, we write what's true. When we write P and not Q and R, we're saying P is true and not Q is true and R is true. That's the same thing as P is true and Q is false and R is true. See what I mean? So it's a complete description. That's what is so beautiful about disjunctive normal form. It makes it really easy to build the IO table directly from the normal form. Like, you don't have to run the values through the circuit. You can see where the outputs are going to be 1 and where they're going to be O because of the nature of the form. Did you need to see the circuit?
Oh, I almost got it right for doing the circuit.
Okay.
I did. Yeah.
Maybe just one little careless mistake or something.
Yeah, I did. Yeah.
Right. Sometimes we go a little blind trying to draw those, but I'm sure, right? I'm sure, right? You know, you got a P, you got a Q. And the nice thing about disjunctive normal form too is because we know, okay, we're going to and together stuff. And then at the end, there's going to be a big fat OR gate. Because the OR happens last, right?
Yeah.
But, this is like 3 different situations where we want to get a 1. We want to get a 1 if it's P and Q and R, or we want to get a 1 if it's P and not Q and R, and we want to get a 1 if it's not P and Q and not R, see? So we know that we're going to have an AND gate for this situation, an AND gate for this, and an AND gate for that, right? So you can just, bend the wires and bring them all close together and run them through an and that's situation 1 right there. Or, here we got to have a not Q. So we can run, here's a solder dot. We can run the Q through a not gate, right?
Yeah.
But then we want P and we want R. So we can pull P down here and bring it in here. And we can bring from this R. And that's situation 2. And finally, for situation 3, we need a not P and a not R. So we can now pull this R through here and through a not gate. So we have a not R. We want regular Q. We don't want not Q. So you can pull from Q and just take regular Q. And we can pull from P, but run it through a not gate. And that gives us the not P. So we've got the not R. We have the regular Q. And then we have the not P. And run them through an AND gate. And that's situation 3. And the output wires from these all get ORed together. And that way, that's the way I check them. I do it like that. I don't know you know how to do that. I actually just drew that for maybe other people that might watch The Office Hour and not know how to do that. That's really why I drew that. Okay, good. Did that help?
Thank you. Yeah.
And Anticott, okay. Anticott, who's got a question now? Anybody got a question?
So my question for this was just like the only time where you're able to identify which one has a hot output is only if the circuit is in a disjunctive normal form, correct? And that way you can just go straight to identifying the part of the IO table with the hot output.
Yeah, well, you can do it though. We can figure out hot output from a circuit. Remember, that was one of the things we did in class. Let me show you. Let's say I don't give you the Boolean expression. Or you get a Boolean expression and it's not in disjunctive normal form. I think that was what problem 2 was. I gave you a Boolean expression. What was it? P and R or?
Not P and Q and not R.
See, that's not disjunctive normal form because this is not a complete description of all the inputs. Like it didn't tell us anything about Q. So what I wanted you to do with this one was to draw the circuit first and then run the values through the circuit. And it's much more time consuming, which kind of makes the point that it's really, really helpful to have disjunctive normal form, because when we have disjunctive normal form, we can go directly to the IO table. But if we don't have disjunctive normal form, we have to run the values through. I'll show you what I mean. So now we want not P ANDed with Q, ANDed with not R. And then these get ORed together, right?
Yeah.
And that's the final output. So it takes a little more room because we have to have room to write on the wires. All right, so if we're trying to, so that's the circuit, okay? So if we're trying to make the IO table, we know we have a P, a Q, and an R. We're trying to figure out S, and we can't do it directly from the expression because it's not in disjunctive normal form. But we can go through these input states one at a time. There's 8 of them, one for each row, and figure out what the output looks like. All right, so let's do that. So the first input state would be row 1, where they're all 1. So P is 1, Q is 1, and R is 1. Okay, so I'm going to do that one in red. So so R is 1, so there's a 1 coming up here through this and P is also 1. What comes out of the AND gate?
1.
1. Ooh, and I'm going to scooch this AND gate over because I need more room. I need more wire. I need room to put what's coming out of these NOT gates before I run it through the AND gate. I gotta have some room here. Okay. What comes out of this NOT gate? If P is 1, what comes out of this NOT gate?
0. Right.
Yeah. And what comes out of this NOT gate? Because R is 1. What comes out?
0.
Yep. And now we're putting a 1, an O, and an O through an AND gate. What comes out?
0.
That's right, because they would all have to be 1s to get a 1 out of there. But now we're ORing together a 1 OR with an O. What comes out?
Oh, 1.
0.
1 OR O is 1. The OR will output a 1 if either of the inputs is hot, or if they're both hot, you get a 1. It's the inclusive OR. The only time you get an O coming out of the OR gate is if both of the inputs are O. But here we got a 1 coming in and an O coming in, so we get a 1 out. So that tells us there's a 1 in row 1. I'm doing that one in red, okay? All right, so now let's do row 2 in black. P is 1, Q is 1, and R is O. All right, so now we're going to see what I mean. So if it's not in disjunctive, see, that's why we love disjunctive normal forms so much. You don't have to do all this work. But if it's not, then this is the job. And this is the instruction I gave everybody, was to please do this by running the values through the circuit. And that's what I meant. We did this, one of our first examples on the day we did circuits. We actually did this. Okay, so again, now P is 1, Q is 1, R is O. So what comes out of this AND gate? Let's look at what's coming into it. The P is coming in, You can go backwards and see what's coming in. The O is coming in. So what comes out of the AND gate here?
Zero.
Yep, because it's a 1 getting ANDed with an O. An O is coming out of that. Great. All right, what comes out of this NOT gate? Remember, that's P is being fed into this NOT gate. P is 1 right now.
So zero. Oh,
That's right. And what comes out of this NOT gate?
so it's one.
Yeah, because R is O, the NOT gate flips the bit. And we've got a 1 on the Q wire. So we've got a 1 coming in, getting ANDed together with an O and a 1. What comes out? It's 1. Like if we want, we can write this, we can write these a little closer. The red 1 came through, and this is a 1. So we're putting a 1 through an AND gate with an O and a 1. What comes out?
An O.
An O, because they would all have to be 1s to get a 1 out of an AND gate. The AND gate has to see all the input wires hot. So an O comes out. So now what comes out of the final gate?
So one.
Well, what's getting fed in? It's the black numbers. This
Zero.
this wire is feeding in this O. This bottom wire is feeding in this O. So what's O ORed with O?
One.
No, it's O.
Oh.
That's the only oh that's the only time you get an O coming out of an OR gate is if you're feeding in a couple of O's or a bunch of O's. Yeah. Okay. All right. Oh, okay, cool. Let's do the next one. Let's do the next one in green. So this is an O. I'll do it in black because we did it in black. It's O. Okay, I'm trying to color code this thing. Okay. All right, let's do the next one in green. P is a 1, so we got a 1 on the P wire. Q is an O, so we have an O here. See how it works? And R is a 1. Let's do a few. Okay. All right. So what's going to come out of this AND gate? Well, let's look. Okay, what's feeding in? A 1 for P is feeding in. A 1 for R is feeding in. What comes out of this AND gate?
A 1.
Yeah, because P is 1 and R is 1, and that's what's feeding into it, is P ANDed with R, see? So 1 comes out of there. Great. Now, P is a 1, so what comes out of this NOT gate?
O.
Good. I'm going to pull the Q is O over here. What it comes out of this NOT gate? It's R getting knotted. What comes out of there?
O.
Good. What comes out of the AND gate? We're ANDing together a bunch of O's. So what comes out of there?
O.
O. But at the final step, and we could probably see it without even doing all that work, I'm just trying to go through it with you. We're ORing together 1 or O. What comes out?
1.
Correct. And that's the 1 that goes there. It's hard to see this is in green here, but that's green. Okay. Let's do another one. Let's do another red one. Let's do 1 O O. So P is 1, Q is O, R is O. See, we're doing row 4 now. You with me?
Yes.
What comes out of this AND gate?
And O.
That's right, because R was O. So we'll get an O here. Okay. Q is O. I'll write it here so we can see what's there. Oh, I just want to see what's coming in here. Okay, so what comes out of this top NOT gate? That's the P getting knotted. What comes out of there?
O.
Yeah, because P was 1, flip the bit, get an O. What comes out of the bottom NOT gate?
1.
Correct. But we're going to AND together O and 1. What comes out?
O.
Great. And now we're going to OR together O ORed with O. That's the one time the OR gate will give us an O, is if we're feeding 2 O's, right? Exactly. So that's an O. So do I need to do more?
No, not for me. I pretty much understand. You already answered my question in a way. I just wanted to know if the only time like you can go straight to the IO table is when you have the disjunctive form. But like if it's in this form or any other form that's not the disjunctive form, then you have to go through this process.
Well, you know what? Now that I've shown you this process, actually you could go directly to the IO table if you understand something about what P and R means. See, when we see here in this particular parentheses, not P and Q and not R, we know everything there is to know. We know P is cold and Q is hot and R is cold. What another way to think about this expression is that P has to be hot and R has to be hot, and it doesn't care about Q. Like this doesn't say anything about what should happen with Q. It only says that P and R both need to be hot. Either Q could be hot or Q could be cold. See, that's another way to understand this. And a lot of students kind of just went directly to that. You see, row 3, P is hot and R is hot, and we get a hot output.
Okay.
In row 1, P is hot and R is hot. We get a 1 for an output. You see, in row 1, Q was hot. In row 3, Q was cold. It doesn't care about Q. As long as P and R are both hot, you're going to get an output of 1. So that is another way to understand it.
Okay. All right. That does make sense.
But the last one, of course, is just for this, because that's it. The only rows where both P and R are hot are rows 1 and rows 3, because every other row, either R is cold or P is cold. So it's so this is P and Q and R, or P and not Q and R, and it turns out that's logically equivalent to P and R, because P and R doesn't care what Q is. So what's the other row where we would get an output of 1?
It's when P is cold and R is cold.
And Q is hot.
And Q is hot.
So there is a 1 here. And that turns out to be exactly the same IO table. It's zeros everywhere else.
Yeah.
And that turns out to be the same IO table that we got when it was in, see, look, P and Q and R, or P and not Q and R. That's the same thing as P and R. So it is, so they are the same. Yeah, they're supposed to be the same. And then this is a very inefficient circuit. It used 1, 2, 3, 4, 5, 6, 7 gates, right? Whereas this circuit only used 5 gates, 1, 2, 3, 4, 5. So yeah, the answer was, yeah, they're logically equivalent, because if you did this right, you got the same IO table.
Yeah.
So there are new, in fact, there's a whole body of study where we work on translating into disjunctive normal form from non-normal forms. And I just have to pick and choose what we cover because we only have so much time. So we did not learn to do that. But if you want to read in section 2.4 of the book, you can learn how to use logical equivalences to rewrite this until it becomes in disjunctive normal form. It's something that we could talk about. I mean, I could show you about that now if you wanted to learn that.
Okay, but like I wanna review the truth tables, because like I have hard time understanding like how to do it.
So what is your question? I'm sorry, I didn't really hear you. You want to talk about truth tables?
Yeah. I'm not
Okay.
really, I wanna
So any particular application of a truth table? Like, do you want to do an argument form? Is that what you were saying?
just the truth table. The argument part is like I can't.
We have 2 main applications of truth tables. one application is to compare two statement forms and see if they're logically equivalent. The other main application of truth tables is to use them to determine if an argument is valid or invalid. Which of those would you like to do tonight? We might not have time to do both, but we can do the
The
other
one like on the special homework.
number 2.
Yeah, special homework on number 2.
Okay, so we used truth tables in both ways on special homework number 2. Like you were supposed to. So do you want to, shall we look at problem 1 from special homework
Yeah.
number 2?
Mm-hmm.
So it was, we had 2 statements. P or the quantity Q and not R. That was statement form 1. Statement form 2 was the quantity not Q and R implies P, right?
Yeah.
So we were asked to use a truth table to discover if these are logically equivalent. The point is, when we make the truth table and look at the column for this expression and compare it to the column that we get for this expression, if those columns are identical, that means no matter what we substitute in for P and Q and R, these are statements, remember, so they could be true or false. It means no matter what statements we substitute in for P, Q, and R, as long as we're substituting in the same statements here as we do here, these will evaluate to the same truth value. That's the point.
Mm-hmm.
Okay, so if we make the truth table, I'm going to set up a column for P and a column for Q. And my pen, why is that so crappy, even though it's full of ink? R. All right, so we're going to need 8 rows. So true, 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 false, 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 false. Sorry about that. It's kind of crappy. True, true, false, false. I'm gonna kind of draw a line through here so it settles my eye down. True, true, false, false, right? And then true, false, true, false, true, false, true, false. Okay, so we're set up. 8 rows. Now we're going to build up to 1. So we need a not R. So I'm going to make a column for not R. And then from there, we can build Q ANDed with not R, right? So I'll make the column for that. And then finally, we'll get P or Q and not R. So that'll be the column for 1. Then to build this, we'll need a column for not Q, because we'll need the not Q. Then we'll AND not Q ANDed with R to get that. And then finally, we'll have not Q and R implies P. So we're going to build up to these. All right, so not R is really easy. It's false, true, false, true, false, true, false, true. It's important to keep these lined up. All right, now we're going to AND together Q ANDed with not R. So we have Q ANDed with not R. So what do we get in row 1?
Q.
Q is true, not R is false. What happens when we AND true with false?
False.
Yeah, I mean, you're asking me that as if it's a question. You need to know how the AND operator works.
Oh, so I
And
think
is only true if both the components on either side of the AND are true. It's like the normal AND. If I say I'm going to walk my dog and I'm going to stop at the store, that's only true if I do both of those. So the AND works just the way we think. So true ANDed with false is false. Got it?
yeah.
But true ANDed with true is true. False ANDed with false is very false.
False.
And false ANDed with true is still false. Row 5, true ANDed with false, that's false. Row 6, what do we get?
True.
At row 7.
False.
Row 8.
False.
Okay. And now we are going to OR together P with this column. Now, the OR operator gives a true result if either component, the two components are the two statement forms on either side of the OR. So P is one of the components. The other component is Q ANDed with not R. See? If either one of these or both, it's the inclusive OR, not the XOR, not the exclusive OR, but it's the inclusive OR. If either one of these components is true or both, then the OR operated statement is true. Got it?
Okay.
So in row 1, we'll look at row 1, 2, 3, and 4. In all 4 of these first 4 rows, P is true. So you can easily see it's going to be true in the first 4 rows by virtue of this component being true. Does that make sense? So you don't even have to think about them much. But now we got to start thinking because the P's are false. So it's going to hinge on the truth value of Q and not R, right? So what are we going to get in row 5 where P is false and Q and not R is also false? What is false or false? Yeah, it's false. Good. What about row 6?
True.
Yeah, because we have a true here. This is true. That's enough to make the OR operated statement true. It's true if either is true or both. Row 7.
False.
And row 8.
It's false.
Good. All right. So this is the final column for 1. It looks like this.
Okay.
All right. Now let's build up to this. So not Q. Well, that's easy. It's false, false, true, true, false, false, true, true, right? We're just flipping the bit of the Q column. Now we're going to AND not Q together with R. So we have to look carefully. We have to look at R and not Q, or not Q and R, right? The AND operator doesn't care, which side. It's symmetric. Not Q and R is the same as R ANDed with not Q. All right, row 1. So the AND operator.
False.
Good. Row 2.
False.
Good. Row 3.
True.
Good. Row 4.
False.
Good. Row 5.
False.
Yep. Row 6.
False.
Row 7.
True.
Good. And row 8.
It's false.
Okay. Now we have to evaluate the if-then operator.
True.
Now remember, if A, then B only fails if the hypothesis is true and the conclusion is false. In all other instances, the if-then is true. So the if-then is true if both the hypothesis and conclusion are true. The if-then is true if the hypothesis is false and the conclusion is true, but it's also true if the hypothesis is false and the conclusion is false. It's always true if the hypothesis is false. So whenever this is false, the if-then will be true. Okay? Remember that? True by false hypothesis. So look in row 1. We have a false hypothesis. So it doesn't matter whether P is true or false. We know that the if-then is true by false hypothesis, okay? That's something that a lot of times students have a hard time with. You just have to get used to it. The if-then is usually true. It only fails if the hypothesis, the stuff on the left of the arrow, is true, and the conclusion, what's to the right of the arrow, fails.
Okay.
Row 2.
True.
Yeah, by false hypothesis. Good. Row 3.
True. Because we
Yeah,
have
because
to.
true implies true is true. There was actually something to check there. Since the hypothesis was true, we had to check the conclusion P. Row 4.
True.
Good. True by false hypothesis. Row 5.
So it's like if it's both of them is false, it's gonna become true.
Yeah, it's true by false hypothesis.
Yeah.
Doesn't matter that the conclusion is false. The hypothesis is false. Like here's an example of a true statement. If Dr. Good is 10 feet tall, then the earth is a star. That's actually a true statement. Why? Because I'm not 10 feet tall. False implies false. If false, then false is true. It's weird, I know. How about row 6?
True.
Good. What about row 7?
So this is gonna become true.
What? This is the one time it fails. True hypothesis. If the hypothesis is true, we have to check that the conclusion followed. This is the one time when it fails. True hypothesis, false conclusion. That's what it takes to make it false.
Oh.
That's the only time the if-then fails. If the hypothesis is true, but the conclusion didn't follow the way it was supposed to, then the if-then is false. Got it?
Yeah.
Row 8.
False. True. True.
Other false. Yeah, true. Okay, right, good. Great. And you know what? Remember at the end of every section in the ebook are problems, and a lot of them have the answers. Remember from doing homework 1? Remember you had to chase around and like do problem 7 in section 1.2. But there was a reason why I had you do that. I wanted to show you, hey, you can use the ebook. You know, you don't have to just do WebAssign. You can go to the back of every section and practice more.
Okay.
So you can go to the back, I think it's section 2.2, when truth tables become a big deal.
Okay. I'll check that out.
2.1 and 2.2, yeah, and 2.3. You can find more problems that you can work. Okay, so now we're ready to answer the question. We compare their columns. Are their columns identical? Do they match in every single row?
They don't match on the row 5, right? Yeah.
They don't match in row 5. They don't match in row 8, right?
Yeah.
Did we do this one right? Yeah, is this right? Not Q. Yeah, okay. Now I'm getting nervous. So these are not logically equivalent because their columns are not identical. So don't forget to answer the question. Like, right? Like a bunch of people like did the table, but then didn't answer the question. All right, you got, so that's like a big deal. When you're like checking your test, look at all your answers and look at the questions. Did I answer the question?
Yeah.
Okay. Sophie, are you good?
Yeah, I'm good. I was just following.
Cool.
Yeah.
Now listen, I'm so glad you came to office hours, and I'm really just dead on my feet. Like I'm so tired. I've been going since like 9 a.m. this morning, hardcore, you know, teaching, thinking, chasing around students, you know, sending emails, you know, giving office hours, blah, blah, blah. So I am happy to do even, another office hour sometime before Sunday night. If you really need it, just email me, or if you want me to look at something that you're working on, you can email me and send me a scan of it and I'll look at it. But for tonight, I gotta call it a day. I'm really tired.
Thank you so much. Have a good
Thank
night.
you, Professor. Thank you.
Hey, thanks for coming to office hours, because now we have a video. I still got 30 more minutes of work because now I've got to scan the notes and get them up, and I've got to process that video and get it over into YouTube. So thank you so much for playing.
Have
Thank
a
you.
good night. Thank you.
All right, see you soon.
Thank you.
Night.